Section: Introduction. In this section, we have explored the impact of ChatGPT on academic writing since its release in November 2022. ChatGPT has been widely used, with around 100 million active users within 3 months of its launch, making it a significant milestone in language models alongside GPT-4. While previous research has discussed the pros and cons of large language models, LLMs, our focus here is on ChatGPT and its influence on the academic community. We have noticed a growing trend of using ChatGPT in academic writing, particularly in abstracts, which are concise summaries of research articles. ChatGPT can generate abstracts directly, and it can be challenging to distinguish between human-written and ChatGPT-generated abstracts. However, by analyzing a large number of abstracts, we can statistically identify the fingerprints of ChatGPT. It is important to note that the presence of the ChatGPT style in an abstract does not necessarily mean that ChatGPT was directly used to create or modify it. Authors may have been influenced by ChatGPT in their writing style even if they did not use it for that specific abstract. This influence is especially significant for non-native English speakers in academia. Before ChatGPT, tools like Google Translate and Grammarly were commonly used, but ChatGPT offers a broader range of applications and greater flexibility. Similar to how AI has transformed other fields like Go with AlphaGo and life science research with AlphaFold, ChatGPT is also reshaping academic writing, especially for non-native English-speaking researchers. To investigate the impact of ChatGPT on academic writing, we analyzed data from the arXiv dataset, focusing on changes in word frequency before and after the deployment of ChatGPT. By dividing 1 million abstracts into time periods and examining word frequency changes, we observed that certain words related to recent hot topics saw a significant increase in frequency. Additionally, even non-specialized words experienced a surge in frequency after the introduction of ChatGPT. The fluctuations in word frequency suggest a growing reliance on ChatGPT in academic writing, impacting not only technical terms but also common words like is and are. These changes in word frequency may reflect the broader trend of increased ChatGPT usage in academic writing, indicating a shift in writing practices within the academic community. Section Summary. In this section, we analyze the impact of ChatGPT on academic writing by examining changes in word frequency in arXiv abstracts before and after the deployment of ChatGPT. We observe that words related to recent hot research topics like COVID-19, LLMs, and AI show significant increases in frequency post-ChatGPT release, while even non-specialized words experience a surge. Additionally, the frequency of common terms like is and are decreases notably after 2023, indicating a broader influence of ChatGPT beyond specific research trends. Section: ChatGPT Simulations. In this section, we aim to delve deeper into the impact of ChatGPT on articles from various fields by analyzing arXiv abstracts from different categories separately. To ensure more accurate results, we divided the 1 million arXiv articles into 20 periods, unlike the previous analysis. We identified the first and last arXiv articles for each period in the appendix. Previous studies have highlighted that ChatGPT has its own unique writing style, which likely influences word frequency. While we can't directly study ChatGPT's word preferences, we can task ChatGPT to refine or rephrase real abstracts from before 2023 and use the resulting data to calculate the estimated change in word frequency hat R_IJ for word I in category J. This change is calculated by comparing the word frequency Q_D_IJ in real abstracts with the frequency Q_D_IJ after ChatGPT processing. We utilized GPT 3.5 in our simulations for 10,000 abstracts in period 14, April 2022 to July 2022, acknowledging that it may have different word preferences compared to the newer GPT-4. Many words showed varying frequencies before and after ChatGPT processing, such as is, R, and significant. We focused on the 4 categories with the highest article numbers: computer science, CS, mathematics, math, astrophysics, astro, and condensed matter, condmat. Our findings support the hypothesis that the decrease in frequency of certain words in real abstracts in 2023 could be attributed to ChatGPT. We also examined the change in word frequency across all abstracts from year T1 to year T, denoted as R_IJ_T, where F_IJ_T represents the word frequency per arXiv abstract in category J in year T. We observed a weak correlation between the word frequency change in arXiv abstracts and our estimated ChatGPT-induced word frequency change across all 4 categories. However, a different pattern emerged in computer science abstracts, showing a strong correlation between R_IJ and R_IJ 2023. While many words appeared unaffected by ChatGPT, some words exhibited a positive correlation in this analysis, even in other categories. Overall, our findings suggest that ChatGPT is a significant factor, potentially the main one, contributing to recent changes in word frequency in abstracts. Our next steps involve modeling the impact of ChatGPT and estimating its effects using real data and simulations. We then considered various scenarios of using ChatGPT in scientific writing, such as correcting grammar, translating sentences, or refining drafts. Different prompts lead to different outputs and word frequency changes. Therefore, we refer to this as ChatGPT impact, instead of proportion, in our analysis. We introduced a simple model to estimate the change in word frequency for abstracts in a specific category after being processed by ChatGPT. This model, though idealized, helps us understand the potential impact of ChatGPT, considering factors like noise, word usage evolution, and user prompts. Section Summary. In this section, we examined the impact of ChatGPT on arXiv articles across different disciplines by analyzing 1 million articles divided into 20 periods to reduce estimation errors. By simulating ChatGPT processing on abstracts, we calculated word frequency changes and found that ChatGPT likely influenced the recent shift in word frequencies in abstracts. Our next steps involve modeling ChatGPT's impact and estimating its effects based on real data and simulations, considering different scenarios of ChatGPT usage in scientific writing. Section: Noise Model. In this section, we examine the noise terms and how they can be modeled in various ways. We start by defining the word frequency for a specific word in a particular category as F_D_IJ, representing the observed word frequency in the data. The term delta_IJ CDOT accounts for noise and variability in word usage that are not directly linked to ChatGPT's internal parameters. We introduce functions C_IJ CDOT to represent the word frequency after ChatGPT processing. The noise from ChatGPT processing for word I is denoted as epsilon_IJ CDOT and epsilon_IJ_S CDOT. The difference in word frequency before and after ChatGPT processing is captured by delta_IJ CDOT, following the same distribution as delta_IJ CDOT. In many data analysis scenarios, having more data points, words in our case, typically leads to better estimates. However, the impact of noise varies for each data point, word, and selecting the right words to include can enhance our estimates. We define a subset of words I_J for abstracts in category J, with a total of N_J words. To estimate eta_J, T, we utilize a quadratic loss function. If we disregard the dependence of G_IJ, T, and She_IJ, T, on eta_J, T, the ChatGPT impact estimate would be given by ordinary least squares, OLS. To address the dependency of G_ij, t, and she_ij, t, on Ada_j, t, we need to make additional assumptions. In case 1, if the effect of Ada_j, t, on she_ij, t, is negligible compared to other terms, we can derive an approximation. Under this assumption, the loss function simplifies, leading to a new estimate hat Ada_g_j, t, corrected for bias and noise. Without knowledge of the distribution of epsilon_ij, CDOT, and epsilon_s_ij, CDOT, we assume Gaussian distributions to estimate the bias. This allows us to express all terms as zero mean noise, except for the bias part. Insights from our results suggest that selecting words with larger values of Q_d_ij, f_*_ij, and hat_r_ij can help reduce bias in our model. Additionally, considering adaptive or iterative criteria for word selection may be necessary, depending on the unknown value of Ada_j, t. In case 2, assuming a Gaussian distribution for delta_ij, f_ij, we define G_c_ij, t, and she_c_ij, t. The loss function under this assumption yields a complex expression for the bias part, leading to similar conclusions as before. By establishing criteria for selecting words in the frequency change analysis, we can simplify the computational complexity compared to testing various word combinations. Our exploration of noise models provides valuable insights into criteria such as Q_d_ij and hat_r_ij. Section Summary. In this section, we explore different noise models for word frequency variations in ChatGPT processing. By considering the impact of noise on word frequencies, we can improve estimates by strategically selecting words to include in our analysis based on factors like Q_d_ij and hat_r_ij. Understanding the distribution of noise terms like epsilon_ij, CDOT, and epsilon_s_ij, CDOT, is crucial for minimizing bias in our estimates and guiding word selection criteria. Section: Approximations in real data. In this section, we deal with approximations in real data. We cannot directly know the true value of f***ij, t, during the ChatGPT era. Instead, we use an estimation hat, f***ij, t, based on word frequency before ChatGPT existed. Our aim is to identify the words that ChatGPT prefers or avoids compared to academic researchers. We assume that these word frequencies should stay consistent without ChatGPT, so we take the average before the ChatGPT era as a reference point. Since real data noise is complex, we did not estimate the variance of epsilon_ij, CDOT. Instead, we used ChatGPT to process more abstracts and used the resulting frequencies to adjust for bias and noise. To validate our approach, we conducted calibrations and tests using a mix of ChatGPT processed and real abstracts. Different words likely correspond to different true values of Ada_j, t, so we created multiple sets of abstract data for calibration and testing. Efficiency is defined for each set of data and word choice requirements. We aim to minimize the error in estimation during calibration. The choice of words may introduce new bias to counteract the original bias, affecting the test results. We calibrated the word set choice by considering mixing ratios proportional to Ada_j, t. We focused on the top 10,000 words in the Google Ngram dataset and used GPT 3.5 for simulations. We used abstracts up to September 2021 for training GPT 3.5 and divided the data into periods for estimation, calibration, and testing. The first 10 periods before ChatGPT were used to estimate f***ij, t. We considered different mixing ratios and eta_n values for calibration and testing. The results showed that word combinations that worked well in calibration also performed well in testing. We normalized word frequency differently in the calibration and test sets but observed similar trends. We tested the robustness of our approach by using different prompts for generating test data. Despite slightly lower performance in quantitative results, our method proved robust. The estimates tended to be higher than the ground truth, possibly due to using a more precise prompt for the test data. Section Summary. In this section, we make approximations in real data due to the unavailability of the true values of f***ij, t in the ChatGPT era, replacing them with estimations f***ij, t based on pre-ChatGPT word frequencies. To validate our approach, we conduct calibrations and tests using mixed ChatGPT processed abstracts with real ones, aiming to identify words favored or disfavored by ChatGPT compared to academic researchers. By using different word sets and mixing ratios, we assess the efficiency of our estimations, considering biases introduced by word choices during calibration and testing processes. Section: Estimation from real data. In this section, we present our analysis of the impact of ChatGPT on real data. We examined the estimates of ChatGPT's influence using different word sets and values of eta_n. After the initial estimation of eta_j, t, we identified three values of eta_n closest to the mean and used their corresponding word sets i_j for a second estimation. This process resulted in the triangle points displayed in the figures. Despite slight variations in the estimates due to different normalizations, the overall conclusions remained consistent. Our estimates show that eta_j, t, remains close to zero until 2023, indicating the reliability of our methodology. We observed a growing influence of ChatGPT on abstracts, particularly in the computer science category, starting from December 2022 when ChatGPT was introduced. Our analysis suggests that around 35% of recent texts in this category exhibit characteristics similar to ChatGPT style when compared to a baseline prompt of "revise the following sentences." In contrast, we found a smaller increase in ChatGPT impact in mathematics, while astronomy and condensed matter physics both showed impact values ranging between 10% and 20%. It is important to emphasize that our measure of ChatGPT impact is relative and reflects changes in word frequency compared to simple prompts. Using more specific prompts, both in real data and simulations, could potentially result in impact values exceeding 1.